so I think by now we probably, I'm hoping most people are able to get on the hub and go through this process of cloning this repository. If you haven't been able to do that, check the Slack general channel, and that should hopefully, there's instructions there. And if you have issues, I know like potentially if you've made some modifications to this or cloned it last night or something, that you may get some error messages with Git. So I'll just do a quick introduction, and hopefully we can, in that time, people can get things rolling. So yeah, thanks Anthony, and thanks for joining everyone. So I'm David Sheen. I'm an assistant professor here at UW in civil and environmental engineering. Let's see, so I guess some background for this tutorial. In I guess 90 minutes or potentially 120 minutes, so we're going to try and cover everything that you could possibly need to know in the Python geospatial stack, which is obviously impossible. So, you know, there's a dedicated hack week that we've done for all of this material. So we spend, you know, a week going through this, and I encourage you to look for those resources. I think I listed them in the latest version of the notebook. There's other tutorial videos like this too, so if you like this format, you can do that or follow on your own. There's also a lot of really good online courses for this material, and there's again some links, and I'll point those out when we get there. But I guess what I'm trying to say here is it's impossible to cover everything that you might need to know in this space in this tutorial. So what I tried to do here is focus on several core concepts and some specific tools or applications that might be useful as you start approaching your projects. So focusing on point data and some of the kind of basic geospatial analysis techniques we might use to work with point data, like ISAT2 data, for example. Let's see. So when I usually teach this stuff, I really like to have lots of interactive discussion. And obviously that's not really going to work with our current situation. So in terms of what we're going to do today, I have a lot of material to cover, and I decided to leave more in and leave a lot of text in this notebook with the hope that you could see something in here. You're not going to absorb it all. So let's just go ahead and acknowledge that there's no way that all of this is going to make sense or all of this is going to be meaningful at this point. It takes time to digest these things, and really you have to practice. You have to try and apply these things to your own problems. And that's kind of the idea with the projects for this hack week. So just want to start off by saying that it's okay. I don't want anyone to feel like they're lost. And please ask questions, or we can follow up afterwards. Yeah, I tried to leave a bunch of text in here as much as possible so that if you are revisiting this later, you can have a little more background. I like to use a lot of links in the notebooks as well. So it's, you know, you can go off on tangents and read and learn more about specific pieces of this. Let's see, what else? I think that's about it. Oh, and one other thing, what I'm showing here, again, this is a sample of the geospatial ecosystem, which we should acknowledge is evolving very rapidly. I mean, even in the past year or few years, the tools that are available to do this kind of analysis have come a really long way. And as the data sets continue to get larger, what we did a few years ago may not really work well anymore. So for this particular example, I'm going to use a relatively small data set. We're not going to do this, and I have a little asterisk here for, you know, this, what I'm going to show you here is not intended to handle billions or trillions of points. There's other tools and other approaches where that's you know, they're better off, or they're optimized for that use case. But what I've noticed and what I've found is that a lot of times, you know, especially when we're learning, it's, you know, dealing with kind of smaller point data sets in terms of grasping the concepts and how the basic pieces fit together. Something with this, you know, fewer points can actually be better in a lot of ways. So, and I guarantee you that, you know, whatever, as you move on in your careers, wherever you are in your careers, this material, I hope that you'll find something here that will be useful for other problems beyond ISAT too. So I guess I'll stop there with the introduction and just kind of get going here. So later today, you're going to learn about data access, and that's hopefully going to allow you to get some samples of ISAT2 data to start playing with. So the question is, all right, we got them, we've filtered them, and next week there'll be some other tutorials on some basic processing, QA, QC, but then what do you do? So you've got your points, you want to do some science. So what we're trying to do here is to work through some basic tools that can help with the analysis, visualization, and interpretation of the point data. I like this concept of exploratory data analysis in terms of asking questions of the data and this concept of data-driven discovery. So you may have a question, a research question as you go into this, but as you do the analysis, new questions and new discoveries will pop up, and hopefully you'll see that kind of approach here. All right, so I think I'm going to minimize this. How's that size? And can people see that okay? Okay, I see a few head nods and thumbs up. I'll try to accommodate that as we move through here if necessary. I realized the other day that a lot of you are probably viewing this on your laptop. I forget, you know, I have an external monitor here that allows me to see things and can look back and forth, but realize it may be challenging to switch between Zoom, where hopefully you're watching my screen feed, and switch between the Jupyter Hub and maybe Slack to post questions. And again, it's not ideal, but hopefully you all are getting better at managing that. So I think the simplest thing to do for now may just be to watch my feed, and if you want, you can execute cells on your own in the hub. Okay, so we're going to try to cover a bunch here. I'm going to try to start with fundamental concepts. So talk about coordinate systems, projections, hopefully a little bit about datums without totally confusing you, geometry, types, etc. So we're going to focus on vectors primarily today, vector graphic or vector data sets. I'm going to talk about basic geospatial data manipulation and exploration using a small, clean ISAT glass data set. So spoiler alert, I'm not going to be using ISAT2 data today. I was, again, hoping that I would have time to do this with some of the new ISAT2 data, but just didn't happen this week. There were other priorities. We're going to use some modern data science tools. I'm going to focus primarily on pandas and geopandas for this because they're really powerful and they allow you to do a lot with exploration, interpretation, and visualization. I'm going to talk about some different approaches for spatial aggregation of points. We'll get into what these mean. I do think it's important to touch on sampling a raster for discrete point locations. I think a lot of you are probably in your projects going to integrate maybe ArcticDem products or REMA products or some other DEM or gridded raster DEM for comparison with some of the ISAT elevations. And so I actually ended up leaving this as an appendix. There's 2 appendices to this very long notebook. So hopefully we'll have time to cover that. And the kind of thread here, we're going to look at elevation change using ISAT data for mountain glaciers here in the continental United States, the lower 48. So we do have glaciers here in the continental United States. They're pretty small, but hopefully you'll learn a little bit more about that as we go through this. Okay, so I think hopefully everyone is good. Let me just put this over here. And I think I don't see anything new in Slack, so I'm just going to keep rolling here. Okay, I'm going to start with a quick Zoom poll here. So I want to ask if you can bring up the participants panel. So if you click that participants button, I see there's 76 of you currently in the call. Can you answer this question? Have you ever taken a GIS course? And that could be you know, undergrad, grad level, maybe an online course, something like that. Give me a sense of where people are as they're coming in. It's totally okay if you haven't. I mean, we have a pretty diverse group here, and often people are not formally taking these classes. Okay. So I'm seeing, you know, maybe like 60-40% on that. Okay. Cool. Well, if you've never taken a GIS class, we're gonna, I'll give you, a few basic things. First of all, talk about what GIS is. It stands for Geographic Information System, and I pulled this from the Esri website, ESRI. They're kind of one of the leading software developing software providers for GIS software. They create the ArcGIS suite. It's one of the more popular, more prevalent commercial options. So it's a framework for gathering, managing, and analyzing data, rooted in the science of geography, and creates many types of data, spatial location, organizes layers of information into visualization using maps and 3D scenes. Yeah, so I'll let you read that. It's the idea is, well, that's the basics of a GIS. It can mean a lot of different things, and what it means within the Python ecosystem is a little bit, it's evolving considering the size of the data sets. There's a lot more emphasis on code and software development than maybe on kind of the traditional GUI-based analysis. So, okay, thanks for clearing whoever did that. So we have just high-level stuff here. We have two primary data types. We have vectors, which consist of point data sets, lines, polygons. You may have heard of a shapefile. That's an Esri format for these vector data. And there's really great resources out there on what these different data types are like. So these are samples of points or multi-point data sets, lines, multi-lines, etc. And again, I don't have time to cover all of this, but hopefully that gives you a sense of what a vector data set looks like. So a lot of the point data we're going to be working with, that's a vector data set. Then we have raster data, which those are kind of what you think of as an image. It's a two-dimensional array of values that represent some property. So that could be elevation, it could be reflectance. So anytime you're using like a Landsat image or some other data set like that, a satellite image, that's a raster data set. They're often provided in, these days, the GeoTIFF format. So it's a TIFF image with geospatial information embedded in the header of that file. It's a great format, and I think later in the tutorial I have some examples of that. So there's a lot more to be said here. There's also ND arrays, or rasters tend to be two-dimensional, and maybe you have multi-band rasters for, say, Landsat 8, for example, where you have different wavelengths of light that are recorded by different sensors on the instrument. But then there's also objects like, say, GCM data or some kind of climate reanalysis data, where you have three-dimensional data by nature. So you could have like latitude, longitude, and then altitude in the atmosphere, but then you also have time as a fourth dimension, and then potentially you have multiple variables on that 4D grid. And so you could have temperature, pressure, etc. So there's tools that are built to work with that, specifically the X-array package that I'm not going to dive into today, but I just want to let you know that it's out there. So a lot of different data types. Coordinate systems, I put some links in here for kind of some of these definitions within the GeoPandas infrastructure. There's really great resources, and I encourage you to explore some of these like free online GIS classes as just kind of basic fundamentals for some of this stuff. It's valuable, it'll go a long way. Yeah, I can't cover it all here. So let's focus on the scientific Python landscape. And I'm going to zoom out here just so we can see this figure. So you may have seen something like this kind of shell of Python, or layered or onion diagram. I don't know what you want to call it, but basically at the core we have the Python programming language. And then moving out from that, we have these different packages that exist within the Python scientific ecosystem. So hopefully a lot of people have tried using NumPy before. Yesterday we learned about Jupyter and IPython. We talked a little about Numba. So these are kind of the next level that are built on top of Python. And a lot of these are written in C++ or Fortran or Java. They're written in some kind of more performance-oriented language, which is not ideal for interactive development, but is great because we can basically leverage these libraries, these compiled libraries directly in Python. So we get the performance of C++ without having to deal with compilers or a lot of the aspects of that language that are more complex. Okay, and I would actually put matplotlib kind of in this shell as well, as including pandas. But so the point is that we kind of have this hierarchical system where like these packages are dependent on Python, and then there's other packages that depend on NumPy or pandas to do things. And so another thing to point out, this is old. This was initially developed in about 2015. There are some things on here that I've personally never used and some things that may have been superseded by new packages. There's another comment about our general ecosystem is it's evolving quickly, and there's always new techniques and approaches to make our lives easier as scientists to do our analysis. So within the geospatial landscape, we kind of have a similar structure where there's a series of packages that are written primarily in C++ or Fortran. You may have heard of GDAL or OGR. These are kind of core geospatial data analysis tools and libraries. Great for working with rasters. OGR is intended for working with vector data. There is a Python API directly. There's also command line utilities that you can use as a Swiss Army knife for some of these GIS operations on the terminal. Geos handles geometry operations. So I believe this was written in Java originally. And Proj handles all the transformations and projections that we might need to do. And I should mention that a lot of the GISs that you may have used, so if you used ArcMap or QGIS or other resources like that, these packages are baked in. They're at the core of those tools as well. They really provide this fundamental capability. But again, it's written in these low-level languages that, while they're great for performance, are not as convenient, and there's a learning curve there. So within the Python landscape, there's a set of kind of Python packages that have been written on top of these libraries. So you may have heard of Rasterio. That kind of provides a Python interface to GDAL for raster data analysis. Great documentation available for this. Fiona provides some of the input and output, the reading, writing of vector data that comes from OGR. Shapely is a package that allows you to interface with this GEOS library for doing geometry operations, intersections, and things like that. And then PyProj, which I think Ben's going to talk about, or others are going to talk about later next week, allows you to get at some of these core Proj functions. So that's kind of the next level in our geospatial onion diagram. And then built on top of that, we have things like GeoPandas, which leverages several of these to make our lives even easier. And actually is built on top of that pandas package, which we're going to talk more about in a moment. CartoPy allows for some really nice mapping, and I mentioned Xarray, again, is leveraging some of these packages under the hood. It's great for multi-dimensional data. It's also really great for well, many different types of data. So I'll leave it at that. I wish I could talk more about these things, but I encourage you to look more into them. And hopefully the introduction we'll do for pandas will help you grasp the data model in Xarray a little bit better in later times. And of course, I didn't have time to make this figure, but maybe we can do that collaboratively at some point. Okay, and I put in some resources here for courses. I mentioned these. There's some really, I really like this one. This is out of the Earth Lab. I believe they're at CU Boulder, but they've put together some really nice courses, which, yeah, Earth Lab at CU Boulder. These are great. They're simple tutorials, easy to follow. So to catch up on some of these things, you can probably find something that is interesting to you. There's also some, I like this course as well. This is another one, how to do GIS-related tasks in Python programming. So there's some nice lessons in here, talk about vectors and rasters, etc. So check those out on your own time. Shameless plug, this is the course that I teach. It's still in the works. I've taught it for a couple of years now, but I've tried to take this hack week model and extend that over a quarter. We're on the quarter system here at the University of Washington. And we'll see some of these visualizations here. I'm still in the process of pushing material up but there's also information if you do teach this stuff, if you're a faculty or postdoc or even a grad student, if you're teaching this, I tried to put in some resources for instructors on how we did this in the background. And a lot of it is sort of similar to what we've used here for this hack week. So if you're going to go off and do this, maybe next year, potentially even remotely, feel free to follow up on that. I mentioned the GeoHack Week. There's great resources there. And I realize I'm kind of wasting a lot of time talking here. So also should mention Pangeo, and there's Anthony or Scott or many other folks who are organizing this event can tell you more about Pangeo. But there's some really nice tutorials. This was the AGU 2019 set of tutorials, and there's actually some really nice canned resources here, for example, on GeoPandas, the stuff we're going to talk about today. You might recognize some of these people. So connect with them if you're curious about these things, and they actually use some more advanced visualization techniques than what I'm going to talk about today. So there's also great resources in here. One more thing about Dask, which I'm also not going to cover, but this can allow you to scale some of these techniques for really large data sets or across clusters of computing resources in the cloud. So I'll leave it at that and get going here. So, well, not yet. So one more note, there's a couple of approaches here for how we can work with these tools to study ISAT2 or to process ISAT2 data. So if you're concerned about efficiency and performance and you've got lots of points, you probably want to rely on things like NumPy, lower level libraries. And I believe next week there will be more emphasis on some of those resources. There are some limitations here. It's less convenient to work directly with the ISAT data and NumPy. Whereas what we're going to focus on today is kind of higher level tools, focus on analysis, interpretation, and visualization. So we're still using NumPy under the hood. So remember the onion diagram, NumPy is down here, and the things we're going to do with GeoPandas are up here, several levels above it. But it provides more convenience and flexibility for rapid analysis, but it also comes with a small performance hit. So it's not going to be as performative as NumPy, but it will make your life easier, I think. So we're going to do number 2, and I'm going with this statement that at the end of the day, I think for a lot of what we're interested in here, a lot of applications, we just want clean X, Y, Z, and time points. We just want position and time. There's many other things that we'll care about. We'll talk more about all the different variables and parameters that you have at your available for ISAT2 analysis. But I think often this is what it boils down to. And so that's kind of what I provided for this tutorial. Is like a nice clean data set that just has this information, and we'll work with it. And just one final thing, as with anything in this world, there are multiple approaches that can be used to accomplish the same goals. And we can't cover them all. You may have a better approach to some of the things I'm going to show. Please reach out to me if you do. But really, you get to the point where you've done this for a little while, and you get to choose, and you know which tool is the right one for the problem you're dealing with. Okay, so ISAT. We've been talking about ISAT2. I think on Monday we did have a brief introduction to the ISAT. It's not ISAT1, it's just ISAT, ISAT glass. I learned that in a review from a paper. Anyway, there was the glass instrument. There's more information later in the notebook about specifics. I encourage you to look at that. Had a much lower pulse repetition rate, but in general, it's a different kind of instrument, but we ended up with point data along tracks. The spot size was much bigger, and the spacing between points was also much larger than ISAT2. We collected billions of measurements from 2003 to 2009. It was operating in a repeat track mode that gave us close to similar reference tracks. And yeah, there's a lot more we could say about this, but let's just focus on the data. So a few years ago, I wanted to evaluate ISAT for the continental United States. I basically wanted to get control points for co-registration. So in other words, taking a bunch of raster DEMs and trying to get them to align correctly so that we could do some elevation difference analysis. I was looking, LiDAR data, and I said, well, we should pull in all the ISAT points to do that as well. So I ended up writing some tools, and I would not recommend using these at this point, but I threw them up here. They're available if people want to look at them. And the primary one was this glass processing. So basically, I pulled down all the HDF5 files that contain the ISAT points over the US, and used this script to filter them down to reduce the data size to what I was calling good points. And if you're curious, that's in here. The actual code is buried somewhere down here. Again, this is in some ways outdated, but it's potentially a template, and I think many of the people on this call probably have their own tools to do this for ISAT data. But it is available, and it's how I produced this CSV, which in the repo is bundled here. And Fernando Perez pointed out that Jupyter Lab has this nice built-in CSV parsing and display capability, which is great. So we'll look at this in a minute. That's where this came from. So what this is, I've got glass points that pass the following filters. So they were near glacier polygons here in the lower 48, within, say, like 100 kilometers. I only provided returns from bare ground, so exposed rock, or snow or ice. So this was using the 2011 NLCD land use land cover data set. So this is a 30-meter product that classifies land cover in the United States. They've actually updated this. I think 2016 is the latest iteration. I also pulled in SRTM data, so that's the Shuttle Radar Topography Mission, and used that as a threshold to get rid of ISAT point elevations that were way off from where the Shuttle Radar Topography Mission measured the surface in the year 2000, mostly to get rid of spurious points and clouds. And then there were other ISAT-specific quality flags. So this is not perfect, but it basically allowed me to take this relatively large data set and reduce it down to what ended up being about 65,000 points. So a pretty small number in the grand scheme of things, but it's a good size for exploring some of these techniques. So I've used it as a sample data set for some of these tutorials. Okay, so you might be saying, wait, I thought this was an ISAT 2 Hack Week. It is, I still haven't, it hasn't happened yet, but I'm hoping that one of the things I'll do next week is actually repeat this, and thanks to Jessica for helping with some of this this effort to bring in ATL06 to update this. And I think having comparing something from SRTM in the year 2000 to shots from 2018 or 2019 should have much better signals in terms of any real elevation change. But I'll be thinking about that if anyone's interested. Okay, so with that, I think I'm going to start kicking this off, and I'm going to run through these interactively. We're going to start by bringing in some things. We're going to import NumPy, pandas, GeoPandas, matplotlib, and some other simple things. I'm going to turn off warnings here. And something we haven't really talked about are matplotlib backends. It can be a little bit confusing, but basically, within the Jupyter Lab environment, there's multiple ways to render figures within Matplotlib, and well, even outside of the Jupyter Lab environment. So what we're going to use today is this widget. It's a little different than what Fernando was talking about yesterday. It's a different kind of widget, but this basically enables the Jupyter Lab environment to give you interactive Matplotlib plots. If we wanted to render these statically so that we could post it on GitHub or something like that and have our figures rendered, we would want to change this to uncomment this line and rerun the notebook with inline, which will render actual, I guess the PNGs or JPEGs in the notebooks themselves. But for today, we're going to do some interactive plotting, so we're going to use this widget. And I will say there are plenty of other options for interactive plotting, but this is the one we're going to use today. Okay, so here's our file. It should be living in the same directory, the repo, as the notebook. So we're going to just define this as a variable, and we'll just do a quick check here. So again, yesterday we talked about being able to run shell commands from within the notebook. So we're going to use the shell head command, which will display the first several lines of the file, and we're going to use this Python variable with that $sign there. So what we get is the output of the head command. I could have done the same thing here. And we get the same output. Okay, so what does this actually look like? We've got a header here, which is a comma separated value, a CSV file. We've got a row here, which is a header of the different column names. So we have decimal year. This is a time ordinal. This is a number of days since some epoch. Don't worry about that for now. We have latitude, longitude, glass Z. So this is actually the ISAT glass elevation recorded for that point. This DEMZ is something that I extracted from SRTM. So from that SRTM mosaic at 30-meter resolution, roughly 30-meter resolution. And then this is a DEMZ standard. That's the standard deviation of pixels in the SRTM DEM around where that ISAT point is located. And finally, we have this land use land cover value. So all of these are in the bare ground class. So that's it. It's a pretty simple, flat format for recording this data. And I think everyone on the call has probably used a CSV before. It's a pretty common data type. Lots of different tools. You can open in Excel, you can open in text files. And it's also, I'll show you, it's very easy to open them with some of these Python utilities. Okay, so some of you know me, some of you have probably never met me, but I'm asking you to trust me here that you should learn how to use pandas. It's, regardless of ISAT2 or what you intend to do for this hack week, it's a really powerful package, and a significant portion of the Python data science ecosystem is based on pandas or uses this data model. So what is it? It's a Python package providing fast, flexible, and expressive data structures designed to make working with relational or labeled data both easy and intuitive, and I would argue also fun. It aims to be a fundamental high-level building block for doing practical real-world data analysis in Python. It has a broader goal of becoming the most powerful and flexible open source data analysis tool available in any language. And every time I read that, I'm like, wow, that's pretty bold. But I think they're actually well on their way toward that goal. And if we go to the GitHub page here, we see that there's currently 232,000 other open source projects that are using pandas. So again, there's something to this. If you haven't used it yet, it's worth learning. And check out their documentation is excellent. This is also a really good example of a really mature, high-level open source package that there's close to 2,000 contributors that have contributed to pandas. There's been tens of thousands of commits. And you can see that people are actively working to develop and improve this package. So pretty great. Okay, so a lot of, one of the best things about pandas is when you're working with tabular data, like a CSV file, for example, or you're working with time series data, it's built for that, to make that analysis very easy. And it's built on top of NumPy, so you get the performance there, but you have these labels. So you can use these, for example, these column names to directly refer to this column instead of remembering, oh, what's the column index? Oh, it's, index 4 or something in my NumPy array. Yeah, so this is an example. And there's lots of good resources out there for learning pandas. And this came up the other day that, some people jump directly into this Xarray package, which, if you haven't, I've mentioned it before, but it's another package used for multi-dimensional arrays or ND arrays. So similar model to the pandas, but yeah, you can see here it's inspired and borrows heavily from pandas. It's great for working with NetCDF, but it can be kind of challenging to wrap your head around this. And there's great documentation, but if this is new to you, start with pandas and then move to Xarray, and it'll be much easier to understand and grasp what's going on. Okay. So let's go ahead and get started here. Let's load this CSV. It's pretty straightforward. There's this read CSV function. Okay, that was fast. It's in there. And if we just, within the notebook, just take a look at what this object is. So we assign that to this variable here. This is a pandas data frame object. And so we can see that we have rows here, 65,000 of them roughly. And we have our columns. And pandas, it knew what to do with this file. I didn't tell it to use commas. I didn't tell it there were some spaces in there. I didn't tell it anything. And it's one of the nice aspects of this. If you look at this function, there's amazing flexibility here. Okay, so I'll just quickly run through a few things. There's, again, this is not a pandas tutorial. There's really good resources for that. But if we look at this, we can see, okay, we've got these columns. Right now there's no missing values. So another aspect of pandas that's great is it really has good support for missing values. Say if we had some nans in here, or maybe we were missing some elevation values, it will read that and intelligently allow you to do analysis around those. One of the things to note is that we have different data types within this object, within this data frame. It's not just floating point numbers. We actually have an int data type here. And that's another one of the really powerful aspects. With a standard NumPy array, you're forced to use all the same data types. So all your data need to be integers, or all your data need to be float. I mean, you can do things with object arrays. There's ways around this, but in general, the performance comes when you have a single data type for each array. But pandas allows you to mix and match. We can put strings in here, etc. Tuples, all of those can be listed in the same object. Okay, so let's kind of keep moving here. We can see, if we look at the columns attribute, we see, okay, it returns a list here, a list of strings. This is just a Python list that tell us what our columns are. And I just want to, if you're relatively new to Python or object-oriented programming, at some point take a break and, well, maybe not now, but like later on, look up the difference between methods and attributes. So this is an attribute on this object, this data frame object, whereas this info, that's actually a method that we called on that contain, that belongs to this data frame object. Nuances there, but there's, you know, something to think about. And there's a reference for the data frame API. I'm not going to open that up now. So if this is confusing, reach out to us. We'll help you get through it. Okay, so some quick ways to quickly preview a data frame head, just like on our the bash command or tail will give us the start or end. I like to use these for just quickly checking to make sure that everything's looking good with what as we proceed. Say we wanted to compute the mean for all the columns, all the values in each column. It's pretty quickly, there's a lot of built-in functions like, say, the NumPy mean function here that can be applied to each column. So we see that the mean elevation for all 65,000 points is 1,791 meters, roughly. There's a whole bunch of these, and you can read about it in the API, or you can do this kind of interactive. So I put a dot in there and hit tab, and get a list of all the different functions and attributes that are available for the data frame object. Okay. You can also apply custom functions. So in this case, we're going to define the normalized median absolute deviation statistic. So you may have encountered this before. If not, it's a good one to learn. I use it pretty regularly. So basically this is a statistic, and for a normal distribution, this is equivalent to the standard deviation. So it gives you a representation of the variability in a data set. But when you've got outliers, if you don't have a normal distribution, this NMAD will allow you to get a much more robust representation of the variability of your data set. So we can define that function here. So it takes an input array, and then this is a constant, and then it returns, this is the formula to return this NMAD. So we have this Python function, and we can just apply that to all the columns the same way we computed a mean or standard deviation. And if we do that, we see, okay, now we've got this NMAD value for each column. And just quickly, if we look up here at the standard deviation, we see that there's a much larger spread in those values compared to this robust estimator. So we know right off the bat that we've got some outliers in here, and we'll talk about that in a bit. And just a quick note, this also exists, and if you can use any function, I don't have to write my own. We can pull in this median absolute deviation function from the SciPy stats module and just apply that directly. So if there's something that you want to use within Pandas data frame, but it's not in the Pandas API at this point, it's pretty easy to do that. Okay, this is another great one. This describe function, it gives you a quick overview of the values in your data set. So we get things like the number of rows, mean values, standard deviation, and then percentile statistics for all the columns in one go. So pretty convenient, great way to just quickly, if someone sends you a CSV, you just want to look at it, this is a nice way to preview what you got. Okay, so I'm going to keep rolling here, and we'll take a break pretty shortly once we get to a natural break. Matplotlib is kind of one of the standard Python plotting libraries. It's useful. I hope most of you encountered that at some point. I think we saw some yesterday. We'll see more of it next week too. So again, I don't have time to like focus on here's all the great things you can do with Matplotlib or NumPy. But we can use built-in plotting functionality within Pandas. So they've wrapped the Matplotlib plotting functionality and make it pretty convenient to just quickly plot up these data frames or components of the data frame. I'm just going to go ahead and do this. So what we're going to do, we're going to call this plot function here on our data frame object. And we're going to pass in some keywords here. We're going to say, okay, the X values for our scatter plot are going to be longitude, and the Y values are going to be latitude. And we're going to plot the glass elevation values with a color ramp. In this case, I'm going to use this perceptually uniform Inferno color ramp. And there's great information about this on how to choose a color map. It's really cool to see how much more attention has been paid to this. And let's see. Yeah, so there's a lot of different ways to display your data. Again, we don't have time to get into all this. We're going to use this Inferno one. These are ideal for portraying linear variations in a particular variable. There's others here that are also usable. There's diverging color maps if you want to show difference values, and I tend to use this red-blue one to show elevation differences. So there's more to be said on there, and Fernando pointed this out last year. Too long didn't read. Don't use jet anymore. If it's a personal choice as always, but the kind of default jet color ramp can lead to interpretations that might not actually be representative of what the data shows. Okay, so basically we've got our first plot here. Again, we're just calling this plot function on the data frame, and we end up with this Matplotlib interactive figure. So what we see right away, we've got a bunch of points. We have elevation values ranging from less than 0 all the way up to above 4,000 meters. If people are less familiar with the geography of the continental United States, so this is the west coast of the United States. Later in this tutorial, we're going to put some context on here so you can interpret this. But for now, it's just a simple plot. Washington State is here, Oregon, California, and we go out here. This is Colorado, so these are the Rocky Mountains. So these are all the ISAT shots that hit the surface and are potentially usable for these mountainous areas in the western United States. Here's the Sierra Nevada, for example. And you can see as I move around here, my mouse, there's an updated display of my X and Y coordinates in latitude and longitude as I move around. It's one of the nice things about this interactive plot. And we can use these tools here to zoom in. So this one here will allow me to draw a little box, and I can zoom in and we'll get an updated display with our updated points here. The axes change. I can pan around in here. There's a little bit of lag. And again, this would not be happy if we gave it several billion points, but for this size data set, it's actually pretty reasonable. And to get back to the kind of high-level view, we can click this little house icon, and that'll take us back to our original view. You can also save out PNGs if you want, and just pop one of these open. There we go. So it's great for just quickly rendering figures. You can also save things directly from the notebook and copy and paste these. But I think that's enough discussion there on the interactive plotting. Okay, so before in this one we were showing the glass elevation values. Let's show the decimal year for each of those points. So it's the same format, same kind of plot, but we're just changing the variable that we're displaying here. If we do that, now we get the same kind of plot, but we see instead of the elevations, we get the decimal years. So there's usable information in here. We see that out here in Western Washington, we have some points from early in the ISAT mission, but also some later ones. So maybe that's a place where we could do some direct comparison of the ISAT elevations, for example. Okay, another useful approach, histograms. Hopefully you've all encountered these at some point. If we look at this, we need to figure out how many bins. Basically, we're going to divide up our data set, and in this case, we're going to create a histogram of time. And if we run again, we're calling this matplotlib histogram function on the data frame, and we're going to use the decimal year values we're going to divide it up for 331 bins. And we end up with a plot that looks like this. So we have time on the x-axis starting in 2003, and the number of ISAT points each week. So if we look at this, we see we see these campaigns start to pop out. This is not continuous, the observations. And if you have more questions about why and how these campaigns were designed, talk to people like Ben Smith or Helen or others who were involved with the ISAT mission. But we see this gives us a representation of the temporal sampling we have for the continental United States, or at least the good points in the Western US. Okay, and we could also create a histogram. Rather than looking at time, we can look at the elevation values. So in this case, we're going to bin up our data in 20-meter elevation bins, and we're going to look at what's called the hypsometry. So the area distribution, the area elevation distribution of our data set. Hopefully that'll make sense here in a minute. So now we have on the x-axis our elevation values. So down here, starting at 0, going up to 4,000 meters. And we're showing the count in 20-meter bins of all of the point elevations that we have. So we see we have a bunch down here near 0, a lot in here in the kind of 1,500-meter elevations, and then over here we get some of the high mountains, the Sierra Nevada, the Colorado Rockies, for example, and way out here somewhere is maybe the summit of Mount Rainier. So just another useful tool, histograms. Hopefully this is all review. One point, I'm going to try to quickly move through this, and then I think we'll take a break. Tom Newman the other day mentioned something about orthometric heights and ellipsoidal heights and datums, and it's always a confusing topic. I still, every time I think about this, I have to go back to resources. But if you look closely at this, we see we have a bunch of points that are supposedly good that have values on, they're like minus 20 meters. Some of these are minus 100 meters. Those are probably not real, but how can we have elevations less than 0? Well, these values that we're showing, those are height above this WGS84 ellipsoid. So this is a nice, clean shape model of the Earth that's defined. And this is not the same thing as mean sea level, which is approximated by what's called a geoid model. Again, this is a confusing topic. There's some really nice resources. I like this one, NOAA. There's a lot of information here. And as with anything, as soon as you start diving into some of these things, you can get lost in the weeds. But basically, the ellipsoid, which is the WGS84 ellipsoid, it's a shape model that we use for the Earth. So we define a semi-major axis and a semi-minor axis to define this thing that's close to a sphere, but is kind of flattened ellipsoid. But then there's this geoid model, which is more of a true representation of what the Earth's shape actually is. And it's represented by this geopotential surface. So if you imagine just distributing water across the surface of the Earth without any continents, this is what the surface of the Earth, the surface of that water would look like based on the distribution of gravity and mass within the crust and deeper within the Earth, etc. I'm not doing that justice, but that's kind of a high level overview of what these things are. Again, look it up, Google, like what's the difference between ellipsoid and geoid, and there's some good resources out there to hopefully help you look at this. So if we wanted to answer this question, how many glass points have a negative value? We could start here. We can just basically, we're pulling out just this column from the data frame now. So here we have the index, and then we have just the glass Z values. And again, we're using these labels to do that. This is labeled indexing. And we're created a Boolean conditional here, so a statement that said, give us, evaluate whether these values are less than 0. And so we end up with, in this case, a lot of these points are above 0, so there are a lot of falses. And we can take that output and then use this value counts function to get a distribution. So we see we have 62,000 points that are above 0 and about 3,100 values that are below 0. Okay, so let's say we want to check the spatial distribution. Again, we can pull these things out. So basically, we're indexing our data frame using this Boolean index. So it's basically just going to return all the true values, all the rows in our data frame that are true. So we do that, and we see, okay, yeah, we've got 3,100 rows now. And sure enough, here are the values. So they're -22, et cetera, moving down. So let's plot that. So we're going to take this data frame. This has returned a new data frame. It's a view of the existing one we have. And so we can run that same plot command. And in this case, we're going to look at the DEM value, or the glass Z values. Okay, and again, we don't have context here. If we had states here, but I can tell you this is Western Washington, this is Puget Sound, this is the California coast, and this is like the Death Valley region of California, which is actually well below sea level. So these points that have apparent negative values are all near the coast. They're close to to 0 mean sea level. Yet we still have these values of -22, -23 meters. So what's going on? This is a plot that I put together that shows the difference between that nice ellipsoid model and this geoid model, which again is like a model of the Earth's where sea level would be across the entire Earth. And we see some pretty big differences. There's places where the two differ by 100 meters or more in some places. So if we look here at the Western United States, we see values that are on the order of, I don't know, -20 meters between the two. And so that's where, if we look at this, that's where most of these values, even though some of these points are right near sea level, they're down on the beach here in Washington State, for example. But according to ISAT2 and relative to that ellipsoid, they're at -23 meters. Yeah. So I don't want to belabor this. It's, again, if you're confused, that's okay. Please ask questions. This is a concept that takes time, and just seeing it more and more, eventually you'll get it. But it's pretty powerful. And just to note that ISAT2, the data we're going to use, will give you elevations relative to this ellipsoid, but they're also using an updated geoid model, this EGM 2008, as opposed to this EGM 96, which ISAT1 used and which I'm showing here. Okay, I think we should probably take a break. So why don't we do that? And let's do a 5-minute break. Let's reconvene. Still a lot to get through, but I think we'll do what we can in the time that we have here. And hopefully I'm not overwhelming people. The rest of this will be more focused on analysis and hopefully things of interest like elevation change over glaciers. Okay, so picking up where we left off with pandas, we can see, well, another thing we can do, we can basically do math between the different columns in that data frame object. So as a reminder, we've got our data frame here, and say we want to compute the difference between our ISAT elevation and this elevation value that I sampled from the SRTM global, I think it was the 1/3 arcsecond model. And I'm going to take an aside here and go down to the appendix, one of the appendices. Okay, so I threw this in here. There's a number of ways that you can actually, for discrete point locations, pull out a value, interpolate a value from a gridded raster or a continuous surface of values like elevations in a DEM or an elevation model. I tried to put in 3 different examples. One's a simple one using this rastereo package for doing nearest neighbor sampling. You can look at the statistics around the point location. So say like within a few hundred meters or however many pixels around your discrete point location, and compute like a mean or a median elevation, as well as get some statistics about the roughness of the surface and the spread of the surface. And then there's others that allow you to do like bilinear or bicubic interpolation, splines, et cetera, where you can figure out mathematically what the value at some non-integer index in your array or your DEM should be. So I put this in here. I threw a sample. This is a 90-meter SRTM product, not the one I used for this data frame we're working with, but something to play with. It's up in the shared drive, so I'm not going to go through this, but if this is something you want to do, say with ArcticDem or REMA or some DEM you've got for analysis, this will give you a few examples of how to do that in terms of the actual sampling. It's pretty straightforward. And then you can take those values and put them into a geodata frame like this pretty easily. Some notes in here. These are some examples of doing the kind of zonal statistics. So taking a bunch of pixels around where your point is and looking at the median or the mean elevation, for example. And then I started this, but I didn't have time to finish it this morning. This is using this map coordinates function, which is pretty efficient for doing, you can specify the order, so bilinear, bicubic, et cetera, to do interpolation at your discrete point locations from an array. There's more on this subject, but hopefully some of these will help. I'd say if you're just new to this, just start with the nearest neighbor for now and get something you can play with. And there's also an example that Jessica and Shashank put together doing some of this for ISAT2 data over Colombia, the country of Colombia, which I think was maybe influenced by Fernando Perez. So here's some examples with ATL06 and doing some sampling of the TandemX global DEM, the 90-meter global DEM product. So yeah, if you're curious, take a look at that, talk to me, talk to Shashank, talk to others. But we're going to do this kind of cooking show style where I've already done that and we've already got these DEMZ values in here where we've sampled the elevation from SRTM. Okay, so let's say we want to compute a difference. We want to compare ISAT to that DEM elevation value. Well, it's pretty easy to do. It's simply subtracting, and we're going to put it in a new column here. And so we do that, and now here we have a new column appended to our data frame where it's the difference between these two values. So yeah, those seem pretty reasonable. They're within a few meters. There's a lot of reasons why these could be different, and we'll talk a little bit more about that as we move on here. Okay, so SRTM was a dedicated shuttle mission in the year 2000 for, I guess, a week and a half, roughly. They were continuously recording data for a certain latitude range for the shuttle orbit. Really amazing mission for the time, and it's really was one of the first publicly available global elevation models. And it's nice because it's kind of a single snapshot in time. It's a week and a half, but for our purposes, if we're thinking about years or decades, it's this day. So we're going to assume a constant day there, and we're going to look at the difference between our ISAT point timestamp. So we see we've got some that are early in 2003 and some that are later in 2009 during the last campaign. So let's compute a difference of this DT value here. So now we've got DH and we've got DT. And if you've been doing cryospheric science or thinking about ice or the ice sheets or glaciers, you know that DHDT is one of our key observables in terms of understanding how these systems are changing. And I put in a parent here because not all of this DH signal is actually real in terms of true elevation value. There's a lot of noise in here, but we can compute DHDT, stick that in another column there. And so now we've got this kind of annualized elevation change rate or apparent elevation change rate for each of our point samples. So we can look at that, and now we're going to use a diverging color ramp to display these, and we're going to set the limits of that color ramp using these Vmin and Vmax arguments. Again, we're just using the same plot function. And if we do that, we see, okay, wow, there's the apparent elevation, rate of elevation. Oh, shoot, let me do the rate here. So there's the apparent rate of elevation change for all of those points. And actually, I'm going to bump this down since we are not using absolute values any longer. So what we see, generally, there's a lot of values that are, kind of around 0. There's maybe some systematic positive values over here, maybe some negative ones in here, definitely some outliers. So some of these things these isolated points are probably not real, but we now have this scatter plot of apparent elevation change for all of our ISAT points. So that's pretty cool. And just if we look at now the absolute, or sorry, just the total, the cumulative elevation change, and we change our color ramp now, so we're, most of these things are now near 0. We see there's these persistent kind of outliers. So some of these values show differences of hundreds of meters, which is probably not real. I mean, maybe you could have like a landslide or something, or a real change in the surface elevation over that few years, but it's probably a bad measurement. So we can quickly do some descriptive statistics for all of these values, and we see that if we look at median, and again, here's that NMAD function that we defined. Up here, we're showing the mean and the standard deviation. We see that on the whole, this data set is, the median and mean values are like minus 0.7, 0.8 meters. So, I don't think the entire country is sinking or has that kind of elevation difference, but we'll talk a little bit more about why we might have this kind of bias in our DH values. Another way, we did the histograms earlier, but we can plot these up, the difference values now, and we see here's the distribution of those values, and here's our kind of median somewhere around, minus 0.8. Okay. Well, another way to look at this and to try and get a better sense of how these values are distributed rather than just looking at scatter plots or histograms. Now we're looking at the elevation of each point on the x-axis versus the observed or the apparent elevation change on the y-axis. And what we see is that there's a nice cluster of points in here, but then we've got these things that are probably outliers, and these look pretty systematic. There's probably some bad tracks in here that we want to get rid of. So there's a lot of ways one can do this. There's clustering algorithms you can use, and we're not going to get into those, but let's just use a simple threshold filter to get rid of these. And so we're going to use a multiple of the standard deviation value to basically say, all right, values beyond, say, I don't know, probably about here, if I eyeball it, and maybe about here or down here, anything below that is probably not real. It's probably an outlier. So in this case, we're going to use these statistics to define that threshold, and we're going to apply that. So basically, we're going to say if the absolute difference between our observed value and our thresholded value is less, basically we're saying, we're applying what could be like, thought of as a bandpass filter. We're throwing out values that are beyond some threshold in both positive and negative directions. When we do that, we see we've thrown out maybe 600, 700 points. And if we plot that up now, we can get a sense of the spatial distribution of where those outliers were. So these black points are the ones that were removed. And here we have the same plot as before, where the orange ones are our inliers, and then everything we've said is an outlier we've tossed out. So definitely cleaner, and if we recompute the standard deviation here, it should be significantly reduced. So the NMAD probably won't change much. In the interest of time, I'm going to skip this. I like to have kind of a group discussion about why we might see these outliers or why we might see these changes. Basically, there's some fundamental differences in how these measurements were obtained. ISAT was a near-infrared laser, had a really big 70-meter spot size for most of the mission. SRTM was a C-band radar instrument, so relatively short wavelength, and it was posted on a 30-meter grid, roughly. It was also acquired in February 2000, so that's the winter, and across a lot of the western United States, especially in the mountains where we're focusing right now, there's a lot of snow on the ground. And the way radar interacts with a snowpack depends a lot on the water content. If it's a dry snowpack, maybe you get the underlying surface. If it's wet, maybe you get something near the surface. Also, how the radar returns from vegetation can vary considerably, especially at different times of year. The fact that this SRTM product was also, there were gaps in the coverage, and so they filled it with this other global elevation product. So what we get is not necessarily from the year 2000, and there's other noisy data sets that could be in there. A lot of other issues, so I'm just going to throw this out there that for the rest of this notebook, what we're doing is probably not, you have to think about all these things and be careful about these. And there's actually some really nice work in the literature of people who have tried to derive corrections for SRTM to account for this radar penetration issue for mountain glaciers across the globe. We're not going to talk about that here, but there's a lot more to be said. And we have some people who are experts in this as part of the Hack Week. So if you're curious or have ideas, post something in the discussion in the chat. Okay, I mentioned we had this land use land cover. So let's see, maybe there's something here like in the elevation change over glaciers, which again, with snow and ice was classified as this integer value 10, versus the barren land, which in theory shouldn't be changing very much. So if we just quickly look, this is the NLCD. We see there were land cover classes for vegetation and grasslands, stuff like that. I wish I had actually kept those in because there's other interesting things we could do. But for now, we've just got ice and rock. Let's pretend that that's what we're looking at. So we see most of our points are actually over rock or barren ground. They're not over glaciers or snow. So one quick thing we can do, we know this. We've got this field that says this is rock or this is ice. But how do we get statistics for each of those independently? So we can use this pandas group by function or capability to compute statistics for each of these land cover classes independently. It's a really powerful technique, and it's kind of this split, apply, combine model. So we're going to split the data into different groups based on some criteria. In this case, we're going to use the land use land cover value. Then we're going to apply some function to group them and then reduce them. We're going to aggregate and compute statistics for all the rock or all the ice. This is a pretty powerful model that's used out in data science these days, and Pandas offers one implementation of it. Okay, so what we're going to do, again, we've got this. We're just going to pull out some values here, and here's our land use land cover. We're interested in looking at the elevation change specifically. So if we do this group by, we're going to group by this column. So we're just going to create two groups. And we do that, and we get this weird thing, which is a group by object. So we didn't actually get anything. The reason for that, this is called lazy evaluation. So basically, we've set this up, but we haven't actually run the computation. We haven't run the calculation. It's nice because you can link together several steps here and then evaluate everything at once. It's a really powerful technique in data analysis, especially if you've got big data sets. They're too big to read into your computer's RAM. But what we need to do here is evaluate this. So in this case, we're going to compute the mean of each of these groups. And look at that, we get a return. So we see that the mean value, elevation difference value over ice was -2 meters, and over barren ground was -0.7 meters. So there's a lot more you could do here. We can define custom functions. This is a list of different functions. We want to look at all these different statistics. We can compute that, and we get all the values returned for, again, for the ice versus the barren ground. And I guess just I'll quickly, I don't want to belabor that point, but we can also quickly plot this up. In this case, I'm actually iterating over the output of that group by object and creating two separate plots showing those values. I did this only because I wanted to have a title here. So this is the ice, or what has been classified as ice. That's the distribution of points. And then here we've got all the apparent barren ground points. Okay. Up until now, we've mostly been talking about pandas, which is great, but we can make these plots with latitude and longitude, standard scatter plots. But what if we want to do more geospatial analysis? Say we want to compute an intersection between points and polygons, for example. We can use this value-added package called GeoPandas. So all the great things about pandas plus geo. So this has become a mature tool. It's still version 0.7, but it's actually become a core package available for this kind of analysis. The goal is to make working with geospatial data in Python easier. And I would agree with that statement. And it does things, you can do things easily that you would normally need a spatial database like PostGIS, for example, to do. So good documentation, nice examples in here. Don't have time, but I'll show you a few kind of tips and tricks on how to work with this. So I talked about this earlier. Under the hood, GeoPandas is using pandas as well as some of these other libraries to do these geometry operations or reprojection. Yeah, let's just keep rolling here. That's not what I need to do. Okay. So first thing we need to do, we need to take our pandas data frame and we need to turn it into this GeoPandas geodata frame. So it's, if you've heard about classes and inheritance, maybe in a programming class before, we can, this is kind of a child or a subset of this data frame class with new attributes and methods available to us. And one of the main things is we have a geometry column where we can store points, polygons, or other kind of standard geometric objects that we can then use for our analysis. So it's pretty straightforward to actually do this. Basically, we take and we create a new geodata frame object. We pass in our pandas data frame, and we specify a geometry. And in this case, we're going to bring in longitude and latitude points, and we're going to use this convenient function to specify what the geometry is for our geodata frame. The other thing we're going to do is specify what's called a coordinate reference system, and we'll talk more about what that is in a minute. Okay, so we run that, and we now have this new geodata frame object. If we look at the type of this thing, we see indeed it's a geodata frame, whereas if we look at the type of our initial data frame, it's just a pandas data frame object. Okay, so we can still use all the methods of a data frame on our new geodata frame, which is great. So we can use that head method. We get the same kind of output here. It's preserved all of the values we calculated above, but now we have this geometry column. And in this case, we have these point objects. So this is, I brought it up earlier, this is a shapely point object where we have the latitude or the x coordinate, sorry, the x coordinate and the y coordinate, in this case, longitude and latitude. We also have this CRS thing, which is basically a coordinate reference system. Maybe you've come across these EPSG values before. This is the European Petroleum Survey Group, is what EPSG stands for. So basically in like the 80s and into the 90s, this group of geospatial folks created this index, this database of common projections or coordinate systems that are used. And it persists today, and it's grown significantly. So there's a whole bunch of predefined coordinate systems you can use. And since we are using the same database, I can hand you something and say, oh, this is EPSG 4326, and you and your software can pull it up and you know what to do with it. You know that that one happens to be geodetic latitude and longitude relative to the WGS84 ellipsoid. Okay, cool. So one of the other things, just like the pandas data frame, we can use this plot function again. So if we just call that on our new geodata frame here, again, I haven't passed any parameters here, so we have really big points, but it looks basically the same as what we did before. We can do this, we can plot up specifying, okay, now we're going to show the glass elevations the way we did earlier, and we get a very similar plot to what we had above. But there's a lot more we can do here. So let's start building on this. So why is GeoPandas good? So we can start to create layered plots here and reproject different data sets so that they'll all plot in the same coordinate system. So let's add some state polygons, for example. And this is another kind of powerful hint. So we could go and maybe to the US Census and download a shapefile, unzip a bunch of files, then copy and paste the name in here. But I don't really like doing that, and we want to create these notebooks that anybody can run, and it'd be great to just do this on the fly. And so what we can do, there are people out there who have posted these like these data sets, like for example, the state polygons. In this case, here's one that is in a GeoJSON format, which if people are familiar with this, it's a basically a text file. If you've ever used JSON, it's it stands for JavaScript Object Notation. There's a lot of good resources on this. I tend to gravitate towards the Wikipedia page. It's an open standard file format. And actually, if you look at one of these Jupyter notebooks, let's just go ahead and do that. Do an aside here. If I just preview this notebook that we're all looking at and modifying, if I look at that, it's actually JSON. And I think Fernando probably mentioned this. He can go into more details, but you can see there's these nested cells. It has the structure of what looks kind of like a Python dictionary in a lot of ways. And it's really powerful and flexible. So we can use the same format to store GeoJSON information. So basically we can store things like latitude, longitude, point coordinates. We can also preserve things like the coordinate system of these points. So pretty flexible. We'll come back to it later in the tutorial, but for now, know that we can just, someone has put a GeoJSON file out there that contains polygons for the states in the United States, and we have a URL that we can just point to. And we can read that on the fly with GeoPandas using this read file method. And it will just load those into a new geodata frame for us. We didn't have to download anything. We didn't have to modify anything. It just pops up and we've got a geodata frame with states, some other attributes here. In this case, this is area. And then we have a geometry column that contains these polygons. So in this case, we've got a mix of polygons and multi-polygon objects. That's because a state like Arizona, no offense to Arizona, but it's kind of a simple shape. There's some pretty rectangular state shapes, so it's pretty easy to represent them with just something akin to a rectangle or a square. Whereas something like Alaska, you've got mainland Alaska and then all the Aleutian Islands, and it's a much more complex feature. And so what you end up using is multiple polygon objects stored in this multi-polygon object. Again, there's great resources from Shapely and Geos on the different geometry types. We don't have time to get through all of these. And because that was defined, the coordinate system was defined in the GeoJSON, I didn't have to specify it. It knows these are latitude and longitude relative to WGS84. So we're great, we're good to go. So quickly, since we're focused on the lower 48, we're just going to throw out Alaska, Puerto Rico, and Hawaii. And let's just do a quick plot here, where what we're going to do is we're going to layer our elevation points from ISAT, and we're going to plot the outlines of the states on top of them. So that's nice. We can do that. It just works, and we have an interactive plot where we can go in and confirm that again, we're still in latitude and longitude coordinates, but we start to get some context here for where the distribution of our points lies. Still don't know, okay, there's probably some mountains over here. In a little bit, we'll get to that. Okay, so those are state polygons. Let's also get some glacier polygons. I'm curious, I'm gonna do another quick Zoom poll and see how many people are still actually out there. If you're out there, and can you bring up your participants panel again? And answer this question. How many of you have ever worked with the RGI polygons, the Randolph Glacier Inventory polygons in the past? Okay, So I'm seeing kind of maybe a 40-60 split in terms of responses. So for those of you who have never encountered these, this is a really cool collaborative community effort to produce a global inventory of glacier outlines. And it's in version 6 right now. There's a call for version 7 to be produced now. There's, I think, something like 220,000 polygons in here. This does not include like the Greenland ice sheet or the Antarctic ice sheet, but it does include the ice caps in the periphery around the ice sheets, as well as the big Arctic ice caps in Canada, et cetera. But it also includes all of our dinky little glaciers down here in the lower 48. There's some respectable glaciers down here too. Okay, so thanks for that input, and I'm glad to see that people are still paying attention. Cool. So we're going to do the same thing. We're going to interactive or on the fly programmatically access this the RGI outlines. So this is a shapefile, and they've bundled it up for different regions. You can look more at the different aspects here, but we're going to get this Western Canada and USA. That you can see they've done this regionally. So if you have another part of the planet you're interested in using ICESat data, you could just go and grab one of these and swap in the appropriate file name. Okay, so what we're going to do, we're going to basically say if we haven't already downloaded, go ahead and grab that file using some standard Python libraries. We did that already, and now we're going to unzip that file. And what we end up with, if we go here to our tutorial, and that's not where I am. I guess I'm in a different, let's see. Interesting. Okay, well, let's see if this works. If not, then yep, it's working. So somewhere in here, I think I'm in where I cloned it. Yep, so we have a new directory called RGI, and within that directory, we have this kind of standard shapefile format. So we've got 4 different files, and we're going to load this, the kind of top level shapefile, if you want to call it that. And I will comment later on the merits or issues associated with the shapefile format. Okay, so if we do this read file and we do a quick preview, we see we've got a new, in this case, a geo data frame now. So we've got a bunch of columns. We have an ID for the glacier in region 2. There's a bunch of other information in here that we don't have time to get into. If we go here, we see we've got close to 19,000 glaciers in this inventory for the Western US and Canada. And Muma Glacier, I like that name. So you can see we've also got this geometry column over here where we've got a bunch of polygons that are ready to go in this GeoPandas. And again, we didn't have to do anything. It loaded it up on the fly because it's a shapefile with a projection already defined. So we can create a quick plot. Again, just with the standard kind of GeoPandas functionality, and we get something that looks like this. So if we zoom in a little bit on, there's something over here. We start to see that, in fact, those are glacier outlines. There's a bunch of individual polygons in here. If we continue to zoom in, this is the coast mountains in British Columbia here, where some of the bigger glaciers in this region exist. In fact, most of the ice in this region is focused here in this part. There's a bunch up in the Canadian Rockies as well. But if we zoom in on our state here in Washington, we start to see some clusters. Here's Mount Baker. These are the Olympic Mountains. Here's Mount Rainier. And one of the things I really like about the in-person Hack Week events is, when we all get a chance to gather in Seattle, you can look out the window and there's Mount Rainier on the horizon if it's clear. But here's Mount Rainier. There's glaciers, some of the bigger glaciers in the lower 48. The Carbon Glacier, which is the lowest elevation one in the lower 48. The Emmons over here is the biggest. It's about 10 square kilometers. And actually in RGI right now, there's a lot of these little polygons over here. Not all these things are glaciers. Those are perennial snowfields. And actually it's one of the items we'd like to take up is to do a better job separating glaciers from snowfields in this index for the next version of RGI. Okay. So let's see, if we update this plot, and I'm looking at the clock, I've got less than half an hour to go. To provide a little more context here, I put in just the countries of the world here, which again is bundled, and we can see, okay, here's the glaciers in Washington. Over here is Glacier National Park, if any of you have been there. And then we get down into the Wind River Range here in Wyoming, and these are the glaciers in Rocky Mountain National Park and in the Front Range. And then coming over here to California, these are the glaciers and snowfields in the Sierra Nevada mountains. Okay, so that's great. We've got this this nice data set, but right now all of our points, and we just care about the lower 48 for now. So let's do some spatial operations here. So let's just isolate the RGI polygons that are within the continental United States. So there's a couple of ways we can do this. We're going to use just a simple bounding box. We're going to use this total bounds attribute for our glacier geodata frame that returns an array with minimum, min, and max longitude and min and max latitude. And we can use this convenience function to just filter those. And if we look at the output of that, it's going to be another geodata frame. Basically, we're just saying only return the polygons that fall within the min and max bounds. And so indeed, we've got, these are just the glaciers in the lower 48. But let's say I just wanted the polygons that are up here in Washington, for example. I went and I drew a GeoJSON polygon around all these glaciers, and I want to get rid of everything else. But it's an arbitrary polygon, has cuts, etc. So how do we deal with that? So let's just make a geometry object. In this case, we're going to create a convex hull. Hopefully people have encountered that before. Basically, it's going to be a kind of a minimum bounding surface around our point data set. So for this particular point data set, it's this blue thing. So we're going to do the same thing for our ICESat points using the geodata frame. And if we look at this, we see that, in fact, yep, we've got a polygon here. And one of the cool things that I'm not sure has come up yet, but you can directly render these geometry objects in the Jupyter Notebook, which is pretty cool. In this case, it's just kind of an amorphous blob, but you can, it's a valuable way to quickly interact with these geometry objects, especially if you're manipulating them. We can also just print it, and here's all the vertices that actually make up this polygon. And just point out that these objects, there's a lot that you can do with them. There's various, so for example, area. There's the area. In this case, we're still in decimal degrees, so it's not as meaningful. But there's these multiple things you can do with these geometry objects. You can compute the centroid, you do the convex hull, etc. So there's a lot more here, and I encourage you to explore some of the powerful functionality that's baked into a lot of these tools. So you do this kind of intersection operation. So we want to say, give us all the glacier polygons that intersect this polygon geometry. And to do that, we're going to evaluate a Boolean statement, or we're going to basically let GeoPandas and really the underlying Shapely and Geos libraries go through and say, okay, does this point intersect, or sorry, does this polygon intersect this larger polygon? And it does that in a very efficient way, rather than us having to say loop through every single one of our glacier polygons and evaluate whether it intersects this larger geometry object. So we end up with a Boolean array here, and we can use indexing on our geodata frame to just give us only the values that evaluated true here. Let's go ahead and do that, and what we see is that we started with 1,900 or 19,000 polygons, and now we have around 5,000 polygons. Okay, and again, just to verify that, look at this, and there they are. There's our small glaciers down here in the western US. Okay, I'm just going to keep blowing through this. I hope people are following, and I hope that some of this is useful. There's a lot more to cover, so let's just press on here. A common thing we need to do is reproject our data. You know, you hope maybe you've done this before in a GIS, but right now all of our points are in latitude and longitude. And say we want to look at things, distances in meters, for example. There's ways you can calculate geodetic distances between points, but for a lot of applications and analysis and visualization, you want to use a projected coordinate system for your specific data set. So the other issue here is that there's scaling issues if using decimal degrees. So the width of a degree of longitude, if you're staying at the equator, is roughly 111 kilometers. But as you move towards the poles, the width of a degree of longitude starts to decrease. The length of a degree of latitude stays the same as you move towards the poles. But imagine yourself standing close to the North Pole. You're covering 360 degrees of longitude, and the actual length of a degree of longitude is on the order of centimeters if you're standing at the pole. Well, I guess you wouldn't stand at the North Pole. Let's use the South Pole for example. Okay. So there's different map projections, and again, this is one of these concepts. It's like the datums. You have to keep thinking about it to really get it. And there's really great resources out there about how to choose a map projection, why we use map projections. Basically, we've got things that exist on this kind of close to spherical planet, this ellipsoidal model that we're using, and we want to display it in 2 dimensions, and we want to analyze it in 2 dimensions on a screen or on a piece of paper in a map. And so there's a lot of ways you can go from that 3-dimensional surface to a 2-dimensional representation. And there's no perfect projection. As you do this more, you'll gain the skills to know, okay, I want to do this, so I need to use an equidistant projection. I need to use an equal area projection. So we'll talk a little bit more about that. Fortunately, it's very easy to do this projection within GeoPandas. There's this function 2CRS, and there's also some nice resources here about coordinate systems and how to go back and forth. And here's the codes, these EPSG codes I mentioned earlier. There's our 43, that's not right. 4326, this is the common one we've been using for latitude and longitude. So look into that on your own. For now, let's just say, okay, we're going to reproject all of our points to another common coordinate system, a universal transverse Mercator, or UTM coordinate system. And these are zones depending on the longitude of the observation. We're going to use this one, which has this EPSG code. We're going to store that in a new data frame. So it's pretty simple. Basically, we say, here's the projection we want to use, and we give that to this 2CRS function, or method of the geodata frame. And it'll take a minute to reproject. So we just reprojected all of our points. And if we look at the output, we see that, yep, okay, we're no longer in that latitude and longitude. Now we have units of meters, and it's in this transverse Mercator projection. If we look at the data frame that came out of that, we see we got all the same columns now, but our geometry column over here, these are big values. These are no longer minus 110 degrees. These are units of meters in this coordinate system. So let's take a look at that. We can replot that kind of using the same plotting function. And we see right off the bat that the plot looks different. The aspect ratio and the scaling of this plot is a much closer representation to what you would see on the surface versus the plots using decimal degrees. Also notice where the origin is. We've used scientific notation here. That's a default with the visualization, but the X origin is somewhere here over near the west coast of the United States. So that's the center of that UTM zone. That's UTM zone 11. But the origin on the Y-axis is way down at the equator, which is where this transverse Mercator projection is defined. Okay, and there's, for notes, if this is new to you, or if you're curious, there's notes on what we just did. So under the hood, we're using PyProj to do this. And I think maybe Ben's going to talk about this next week, but this will come up repeatedly. This reprojection of points is a pretty common operation. Yeah, there's more information about Proj and what's actually happening and how these transformations are actually applied. So I encourage you to check out some of those resources. And it can get pretty complicated. Going between WGS84 and UTM lat-long to these meters is pretty straightforward. We're using the same ellipsoid. But it can get really complicated. We have different datums. Plate tectonics is a thing, so time becomes a component. And fortunately for us, Proj takes care of all that. And it's actually undergone some significant improvements in recent years to do a better job with some of these complex aspects. Okay, so we did that UTM, but it's really not a good choice for what we're trying to do here. we use zone 11, or yeah, we use zone 11 here, but our point data actually cover a huge part of the Western US. So we're going to get increasing distortion the farther we move away from the center longitude of our projection. And so what we're going to do, we're going to define a custom projection. This is kind of, if this is new to you, don't worry too much about this, but we're going to use an equal area projection to minimize distortion over the extent of our points. And the way you do that, you define it with standard parallels. There's a bunch of text in here, so again, go back and check that out if this is new. I'm just going to keep moving here. And we're going to create a proj string which defines this projection. So it's just a string, like a Python string, but we have these keywords that define our projection. And that's kind of all we need right now. We're giving it these standard parallels and an origin, a center latitude and a center longitude. And we're going to do the same thing. We're going to reproject our points, but we're going to use this projection. And we can just directly feed that proj string to GeoPandas, and we see that it comes out, and again, we've got different, these are meters now, but we have a different origin of our coordinate system. I'll just store that for later. So we'll just do a quick summary, and then hopefully, I think we move on here. Yeah. So this is kind of a plot of these three side by side. Hopefully it will be a little informative. So we've got the geodetic latitude, longitude with decimal degrees over here. It's what we started with. Here's our UTM projection, and then over here is our custom equal area projection. And they're not that different, but you can right away see the differences in the aspect ratio of the projected coordinate systems versus this one. And if you look carefully, and it's subtle, but there are differences between these two, especially as you get further away from the origin here. Some of these points, there's more distortion out here in Colorado in terms of like distances between points or the angles between points. Whereas over in this one, we'll do a little bit better job, and an important part of this projection is we can compute any area anywhere within this projection, and we know it's true. We know that that's the true representation of the area of a polygon or something like that. It'll come in, why that's important will come in later. Okay, let's move on now to this concept of spatial aggregation. So say we've still got all these points and we've just been looking at them, but say we want to compute values for like glaciers or for the state of California or something like that. You can aggregate information for polygons and compute statistics. And a quick way to do this is with what's called a hex bin plot. It's a nice way to visualize point density or some other metric like the median elevation on a regular grid. And later in the week, Johan's going to talk about some more complex interpolation and gridding options, which are valid and useful for certain applications, but there are times when you might want to use this hex bin approach as well. There's a lot of reasons why we use hexagons these days. It's actually kind of an interesting study. So basically, hexagons are the closest thing to a circle, closest shape to a circle that can actually be continuously tessellated on a surface. So we can use squares, like this is a standard raster. So if you've loaded up an image or a DEM or something, we have pixels that are rectangular or square. We can use triangles, but in the sense, we can define a bunch of hexagons that are continuous across the surface, and it's the closest thing to a circle, and there's a lot of reasons why that's valuable. So check this out, and also there's this, gotta mention it, Sarah Battersby is down at Tableau here in Seattle. She wrote this paper, which I think she managed to get one of the better journal article titles published that I've seen. So if you haven't seen the movie Snakes on a Plane, well, I don't know. There's a movie called Snakes on a Plane, but this is an article called Shapes on a Plane. And she goes into these issues of projections and how to think about statistics in different projections. So, okay. It's very easy to make these things. I'm just going to move through them. So we're going to define a grid of 40 bins in the X and the Y direction. And we're going to call this matplotlib hexbin function here. We're going to feed in the X values, the Y values. And in this case, we're just going to look at the point count. So they effectively give us a density in each of these hexagon bins. And so what we see, here's the plot. Again, this is using our projected coordinate system. And we see that some of these cells over here have very few points. This is a logarithmic color ramp here, so there's maybe a few points, but others, like some here down in Idaho, some in California, they have hundreds, potentially even thousands of points within that area. So we get this kind of binned point density metric here. So that can be useful for visualization and inspection. We can also look at the, say, the median elevation of all the points that fall in those bins. So again, we've got the Colorado Rockies over here, low elevations out here near the coast and the Sierras. So it's another way to analyze these statistics on kind of a regular grid. And again, we can also use interpolation approaches for like kriging, for example, which we'll talk about next week. So lots of different ways to do this. Here's one. Okay, so another strategy that in this case we defined a regular grid and we looked at statistics for this regular grid. But let's say we wanted to do these same things, like get the median elevation or the count of points for each of those polygons, those glacier polygons we looked at earlier. How are we going to do that? There's no like convenient pandas or geopandas function to just like call that and have it work like magic. So can we answer this question, I guess? Let's frame it this way. Can we identify Conus Glacier surface elevation change that occurred between 2000 and our ISAT points? So we've already done the work to get DHDT values, but now we need to look at the DHDT values in each glacier polygon. So we could loop through these things and do an intersection like what we did earlier, but it's inefficient, doesn't scale well. So what we're going to do is called a spatial join between the points and the polygons. And then we're going to go back and redo this group by and aggregate thing to compute statistics. So you may have come across this before. If you've ever thought about databases or if you've taken a GIS class, these are common applications. So you can join things based on like an attribute, say the glacier polygon ID, the RGI ID. You can join that with other tables that you might have in a database. A spatial join does that spatially, so you don't necessarily have a particular field you're joining on, but you're joining based on spatial relationships between objects. And I realize I'm sitting here waving my hands around. I don't know if people are actually seeing that, but if you are, maybe that's helpful. I'm kind of showing polygons like this. Again, I really like when I do these, I like to have interactive discussions, but we're doing the best. Like Zoom can be good in some ways too. So, okay. Again, lots of resources out there from GeoPandas on how to do this, but let's just show a quick example. So the first thing we need to do, we want to get everything we're going to join together in the same projection. So we've already created the ISAT points in our equal area projection. Now we're going to reproject the polygons to match that. And it's the same to CRS, and in this case, we're just directly saying, okay, our ISAT points, whatever the coordinate reference system is, we're just going to directly pass that in. And if we look at this, this is an optional step. We've got a lot of columns here, and we don't really need them moving forward. So we're just going to specify the ones we're interested in. So we're going to look at just the elevation, the DHDT, and we want to preserve the geometry for the ISAT points. And then we're going to look at the RGI polygon ID, the name, and the geometry. So we're going to create these separate views of the larger data frames. We'll call them light. And if we look at them, we see, okay, these are our points now. We've got 65,000 of them. We got the key attributes we're interested in. We still got that point geometry in our projected coordinate system. Okay, so let's just do this. Let's join them together. So we're going to basically we're going to keep the points as our kind of primary geodata frame, and we're going to append values from polygons, the glacier polygons that intersect those points. And we can do it. Takes a couple seconds here, and this is going to scale based on the complexity of the polygons and how many points you've got. But for this case, since we've got 65,000 and then something like 5,000 polygons, took 5-10 seconds. And we see the output, we've got a new geodata frame, but only 822 points were actually returned. So those are the subset of ISAT points that actually intersected one of these RGI polygons. And for each of those points, we know exactly which polygon was preserved. And we can see that for these 2 points, they're separate ISAT shots, but they intersected the same glacier, this Noisy Creek Glacier, which is up here in Washington, North Cascades. Cool. So that's great. We did it. But how do we make sense of this? Well, let's just start checking it out. And so we see we started with 5,000 glacier polygons. We started with 65,000 points, and we've ended up with a relatively small subset that actually intersected them. Let's see which of these glacier polygons actually had the most points. So we can use this value counts method on the this column. So basically here we've got a whole bunch of points that intersected this polygon. And we see that this guy here, the most, we have 49 points over this glacier. And then there's a whole bunch of other glacier polygons that just have 1 ISAT point. Not great, not really a good sample for measuring elevation change, but let's pretend that we've got usable data here. So let's say we wanted to figure out which glacier has the most points. There's some indexing we can do here, but basically we're gonna isolate this guy. So it has the most points, 49 points intersected that one. And we're gonna pull out the record for that particular glacier. And we can see here's all the attributes from the RGI. And oh, there's the name, it's the Swift Glacier, which maybe you know of, maybe you don't. But let's, again, we can look at it here. Here's the geometry for this record. And you can see we have this thing that, yeah, I believe that's a glacier, kind of an amorphous blob there. But I still don't know where it is. So we can quickly use what, there's a lot of different ways to visualize these things. We've mostly been using Matplotlib. We can use an interactive iPly leaflet map. It's one option, and this pulls in base maps, these tiled base maps. So this is a really powerful thing that's available to us. You've all used these. If you've ever used Google Maps, you've clicked and dragged or zoomed in and out. It's loading in tiles on the fly at different zoom levels based on where you are within the map. So there's a lot of free resources. OpenStreetMap is one. They have a lot of these base maps that are tiled. And you can read more about this. Google Maps has a lot of different, you have the roads, terrain, satellite data, etc. But it's a really efficient way to serve up just the tiles at the resolution that you need, which makes interactive visualization pretty powerful. Okay, so we're just gonna do this quickly. Point out there's a lot of different base maps you can pull in with some of these tools. In this case, we're gonna use this Stamen terrain map, which I like, but there's a bunch of others, including some of the OpenStreetMap tiled base maps out there. So check those out. There's also some great resources from NASA for like tiled MODIS data, for example, that you can pull in. And if we quickly make this, we can basically plot up the center latitude and center longitude of this record. So I've defined a marker in this iPy leaflet map and just displayed this thing. And we see that's where that center latitude and longitude is. And hopefully people recognize this mountain. Maybe you don't, but this is Mount St. Helens here in Washington. There was a large catastrophic landslide and eruption in 1980. We just celebrated the 40th anniversary of that recently. But we see that this Swift Glacier is actually here on the southern flank of Mount St. Helens. And as with some of these other maps that you're used to playing around with, we can zoom in and out here. Can double click to zoom in. So it's a nice way to kind of get these interactive visualizations. One caveat, I would not put in hundreds of thousands or millions of points in here. This is not the right tool for that. Although you can nest these things. So at different zoom levels, you'll see clusters of points, and maybe you've interacted with those before. So there's a lot of flexibility. That's a basic intro there. Got 3 minutes left. So what we're gonna do here, we can zoom in quickly on Washington State. And you know what, I'm gonna skip this. So what we did earlier, we did this spatial join. So we've got 800 points left over. We know which glaciers they fall on, but now let's compute statistics for each of our glaciers from all the points that intersected that glacier. Okay, so we'll go down, and now we need to go back to that group by and aggregation thing that we talked about earlier. So again, here's where we are. We've got 800 points. If we group by, in this case, we're going to group by the glacier ID. So we know that all these fall in Nosy Creek. We do that. Again, we've got this thing. Wait a minute, this didn't work. Well, we need to actually evaluate that. So if we look at the mean elevation values, the mean DHTT values now, by using the mean function here, we see that we've got a new data frame with all the polygons, each individual one, and the mean values for each of those polygons from all these points that intersected those. So we've effectively aggregated statistics for each of those. We can do more sophisticated things. In this case, we have a dictionary with a bunch of different stats we want to compute for each glacier. And we can group by and then aggregate, passing in that function. This would also work if I had given it, np.mean, that would work. But in this case, we're going to use this dictionary. And if we look at it, now we've got a lot of, more interesting statistics for each polygon. We've got elevation values, we've got DHTT values, as well as different metrics on the mean and the variability, the variance. So let's just keep moving here. If we try and plot that, we get something like this. And when we look closely, we realize that our geometries are gone. We've lost our polygons. So we need to add those back in. Not a problem. We can do that here. And I'm just going to move through this. Now we've got the same data frame, statistics here, and our polygons are back. And we can make some final maps here. So we're going to introduce two new packages here. We're going to add a scale bar. So this is nice because it adds a dynamic scale bar to these plots, in like 10 meters, 100 kilometers, et cetera. And it'll scale as we go. And another option for bringing in tiled base maps. So we're going to use this context tiley package, which will bring in and statically render these things. Both of these are really valuable if you want to make a figure. It's for a publication or something like that. You can render these, you can specify the DPI or the resolution of the figure, and get really nice high quality products. So in this case, we're going to use this add base map function from context tiley, and we're going to pass in our coordinate reference system and the axes for matplotlib. So we're going to say, we know our projection, we know the extent of the data we're trying to plot from the plot we've already made from the axes. And this will go and fetch the tiles. In this case, we're going to do those same terrain maps. And you can specify the zoom level. In this case, we're just going to let it decide based on the extent. Then we're going to add a scale bar to our plot. In this case, 1 pixel, or we're using units of 1 meter here, so we're going to do that. And I encourage you to read more about each of these individually. But if we just look at this quickly, we now have this nice context. We have this tiled base map in the background, and it's been reprojected into our coordinate system that we're using here. So that's pretty nice with our scale bar up here, which again, we've got these axes labels, so it's maybe not as useful. These are in meters, but we can chop those off and just have this figure with the scale bar if we wanted. Okay, so let's make this final set of interactive plots here. So what we're plotting on the left, this is the number of glass shots for each polygon. And on the right is the median DHTT value for each polygon. So let's go ahead and zoom in on some things here and see if we actually ended up with anything useful. So as we zoom in, we see here's Mount Baker up here. This is Mount Shuxon. So at Mount Shuxon, we actually had a fair number of points. And if we look at them here, we see, okay, here's a bunch of our ISAT points. And maybe there's actually a reasonable sample across each of these glaciers. It's not great, and I wouldn't necessarily trust these values. So the color of the polygons now, this is a chloropleth map. It's showing the median of all these points that fell within that glacier. And we can see there's values closer to 0 here, whereas a lot of these points are much more negative on this particular glacier. And if we look closely, we see that this guy here actually had close to 40 or 50 points intersecting it, whereas some of these smaller ones, there's 1 point over here. So probably not the most representative sample, and I'm not sure this is actually a glacier. This might be one of these perennial snowfields. But this is a kind of a quick way to show these data and represent these data. And if you want, you can go and play around and zoom, look at some of the different glaciers here. Again, not very big, but you get a sense of the distribution. And I wouldn't publish anything like this. Well, there's something to be said for publishing non-results, but at least we've got this tutorial and people can look at this if they want. There's more here that I was just looking at. Can we extract any additional information? Short answer is no. But if you wanted to look at relationships like glacier area, number of points, etc., you could do that. Okay, I'm over time and I don't want to eat into the break, but one final point, we can easily export this thing that we just made and we're interactively viewing here in the notebook. Say we wanted to give it to a friend, or we wanted to look at an ArcMap or QGIS. We can use GeoPandas and under the hood Fiona to do that. So there's all these different formats, including Esri shapefiles, GeoJSON, some of the things we talked about. If you've taken a GIS class or not, you've probably used shapefiles. Again, this is kind of the soapbox, and there's others who agree from this. Please stop using shapefiles if you can, and encourage others to do so. There's a reason why it's not really an ideal format. It's old. It's been around since I think the 90s. We have much better formats that are available to us. GeoPackage is a great one, and that's what we're going to use here. Or GeoJSON is another nice one. So please check that out, and happy to talk more about that. But creating this GeoPackage file, which is just one file, is very easy to do. So we've got our geodata frame, right? This is the same thing. We've got a record for each glacier polygon, got a bunch of statistics, different attributes, and then we have the polygons stored in here in this geodata frame. And now we've written it out to this GeoPackage. And if we go over here to the folder, there we are, we should see, there it is. It's now this standalone file. And one of the cool things we can do in Jupyter Lab is we can right click on that and say download. And that will immediately pop up on my local computer. It's pretty small, it's less than a megabyte. And my operating system says, oh great, we can open this with QGIS. And I believe that happened, it's over here, but just to show you that this actually works, it loaded that file, and if we zoom in, we see we've got the same polygons here, so we're looking at Mount Shuksan again. And if I, kind of using the standard GIS tools, if I look at this, I can pull up the attribute table, and indeed, we have all the same statistics we just computed, as well as other metrics here. So pretty cool. You can do more advanced analysis within tools like QGIS, say spatial selection, that kind of stuff. But now you also know how to do it in Python. And there's more notes in here. So glass, this is not the right tool for these tiny glaciers. We knew this, but what we've demonstrated here could be applied to ice caps or other locations that do have a good sample where you could actually do science. And there's really good examples of this in the literature. Alex Gardner and Andy Cobb are two names that come to mind. They've led papers that have done this for global glaciers using ISAT. So I think I'm going to stop there. I will say, if you're curious about sampling rasters, there's this appendix. And then in terms of projections, I think a lot of us here are working in the polar regions, maybe on the ice sheets or sea ice. I put in some notes here on map projections and distortion issues with the commonly used stereographic projections. So it took me a while. I wish I had known this when I started my PhD, so I'm happy to talk more about it. But it just kind of goes through some things we might not think about when we're doing our analysis and what that means for, say, calculations of mass balance or elevation change, and things that we can do to improve that.